Hi, welcome to the Topology optimization session of the First Steps course. Here you will learn how to optimize a topology for a specific load step. You will run a model optimization for the cantilever beam from the geometry generation session and input a topology variable. This will help you to understand how you can set up the topology optimization workflow for your own products. No matter what kind of topology optimization we want to run, we always need the same four inputs, which is the constructed model. If you would like to know how to construct a FEM model that we can use for this topology optimization, have a look at the FEM analysis video, please. And then also the solid part of the design space. Also go to the same video to have a look how this is created. Then the element size of the mesh of the solid part, and then also the load step. All of these you find in the FEM analysis video. I will quickly blend them in. So this is our model. As you can see, this is the start node for the connector elements, and I use the default input, which is the center of the target geometry. So that's the same for all of us. Then this is our design space of the cantilever beam, the solid part. The element size is 1. And then we have our load step, which has a force and a fixed support. Okay, so in order for us to perform a topology optimization, we have to go through different steps. The first one is to define the topology variable. Then we will go on to define the constraint, and here we actually will have two different versions. So we will first define the constraints for a dimensioning topology optimization and then for a non-dimensioning topology optimization. The same goes for the third step, which is defining the objectives of the optimization. Again, first the objectives for a dimensioning topology optimization and then for non-dimensioning. And lastly, we will run the optimizer and have a look at the results. Before we start with our first step, I'm just going to explain real quickly why we will have those two streams, the dimensioning and non-dimensioning optimization. So the dimensioning topology optimization is ideal if we have volume AM parts, and we will get less discrete designs. And this process is ideal to be reconstructed with the quad remesher process. And then on the other hand, we have the non-dimensioning topology optimization, which will give us a very discrete design, which is ideal if you're not looking for a volume IM part, but more of a rod-shaped design, which you can then later use for the skeleton process. So you will just get the skeleton or the lines of those rod shapes and then perform a cross-section optimization. So let's get started with defining the topology variable. We have our inputs here, which is already a name for the variable. Which is given, and then we will provide the solid part. These two inputs are already sufficient for the component to run and create a topology variable, but there are many more options to define our variable. And we would like to also use the minimum and maximum diameter inputs. And I will use the element size for that. And I would like 3 times the element size as the minimum diameter. and then 6 times the element size as the maximum one. All right. And now also I would like to define a mirror symmetry plane. So if I blend in the design space, I would like the result to be symmetric to this plane, which you can see here. So I will plug in this plane into the mirror symmetry input. If you have a radial symmetric design, you can use the cyclic symmetry plane input or cyclic repetitions. And then also if you're casting a part, the raw direction is an interesting input to use. But yeah, for our application, these inputs are sufficient and we are ready to go on to our next step. In our second step, we will define which constraints our optimization needs to meet in order for a feasible result. And we will start with the first stream, the dimensioning topology optimization. So in the dimensioning topology optimization, we will optimize our part regarding the stress and displacement with constraints. And then we want to minimize the mass of the part. And as I mentioned before, the load paths of our design will not be discrete. However, a great advantage is that we can directly convert the Topo result back into a solid body using the quad remesher topology reconstruction process. So we will use the stress response and the displacement response component, plug in the load step. If you want to, you can also define separate names, but yeah, because we are doing an educational example here, which is very small, it's not necessary. In a larger project, it definitely makes sense to keep an overview and defining names everywhere. Okay, so now we will use the Fem constraint component. And here I actually prepared a name because we have different constraints also for the non-dimensioning topo. And this is the response for the stress constraint. And then we have an upper bound for the stress plugged in here. And then we will use another Fem constraint component for the displacements response. And we also have an upper bound defined here. So now the optimization knows that these are the maximum values that are allowed to be reached, and if the values are exceeded, then the design is not feasible. Now we can just plug both of these into this output and are ready to take a look at the non-dimensioning topo. This topology optimization is stiffness based using the volume fraction response, and you will get very discrete load paths. However, you will need further processing because these are not dimensioned yet. So this constraint is ideal for a reconstruction process using the skeleton process. If you define those lines, these discrete lines, you get a rod-shaped result, but then you have to do a cross-section optimization to actually get the ideal result for the stress. Okay, so let's get this volume fraction response on here. We will give it a name and a model part. So our final design of the optimization will be constrained by the volume of that design. We will also use the Fem constraint component, plug in that response, give it a name, and now we will set an upper bound. So this is set to 0.1, which translates to that in the end our design is at maximum supposed to have 10% of the original volume. And if we plug this into the output, we are good to continue to the next step, which is defining objectives. Again, we will start with the upper stream, which is the dimensioning topo, or the first stream. And I think I mentioned before, we want to minimize the mass for this design, which is why we'll use the mass response component. It only needs a name, or it doesn't even need a name. There's a default value in here. I won't plug in a name. I'm happy with the default value. Mass response sounds good. And then I will use the Fem Objective component, plug in this name and this response. And now I can set a goal. So I want to minimize the mass. I could also choose to maximize it. And I can plug it into the output. So yeah, the optimization will try to find a design with the smallest possible mass while not exceeding the values that we set here in the constraint. So this maximum stress and the maximum displacement value. All right. So now that we have defined this objective for the dimensioning topo, let's go down to the second stream, the non-dimensioning topo. For this stream, our objective or our goal for the optimization is to find the stiffest possible design, and we want therefore find the design that has the smallest response to the load step. And we will use the weighted compliance response component, use that name and enter the load step. And here you would have the possibility to enter different load steps and weigh them differently. However, we only have one here. It's a simple example. That's definitely enough to get into the whole topic. Okay, and now we also need the Fem objective. We will plug in that response. So we want to minimize the response of the design to the load step, therefore get the stiffest possible result. You could also set it to maximize, and now we would be looking for the most flexible result, the result that has the greatest possible response to the load step. As we're looking for the stiffest result, we will set it to minimize and can plug it into our objective output. Okay, so now in the fourth step, those different streams for the dimensioning and non-dimensioning topo meet again. So no matter which of those optimization you want to run, now it's the same process again. So now to actually run the optimization, you need the OptiStruct optimizer, plug in the name, the Fem model that we got all the way from here, from the input. We haven't touched it since. Here we are. And then the constraints and objective. So I've prepared here the constraint and objective for the dimensioning topo, and here for the non-dimensioning. You can choose which one you would like to run. I will go with the non-dimensioning one and connect them to here. Now we also need the topology variable, which is all the way here. Just use that wire and drag it all the way here. And now our OptiStruct optimizer starts running. So what the optimizer does is calculate a density distribution for all elements in the model, assigning them a density between 0 and 1. That value is called the ISO value. And it gives information about how much this individual element contributes to the stiffness of the model. So 0 means it doesn't contribute at all. 1 means it highly contributes. You can also use this drop down and set maximum iterations here If you don't want to wait as long, you can decrease them. You can also set to different number of processors if you don't want to use all processors of your computer. Enter a different solver path if, this might be interesting if you can't find your solver directly. And also enter arguments to further individualize your optimization. Alright, so the component has run through and we get our result, which is the result of the last optimization iteration. And then also, if you plug in a panel into the info output, you can read that the operation is completed. And if you connect it to the successful output, you will read true if there has been any issue. If the optimization didn't work or you didn't get a license, you will read false here. So this is always good to check. In case you don't have an Altair license and you couldn't run the optimizer, here you get both of the models prepared. And now we can actually continue to display our result. Before we do that, I will select everything and hide it so that we only see our result. I will use the result isomesh component right here and then use the isovalue slider, which filters the elements. So right now it's set to 0.8 and it doesn't look good, the result. And what it means is that every element that has an isovalue below 0.8 is not contributing to the model right now, or to the isomesh. It's not included. So let's go down a little bit, maybe to here, or even further until you're happy with the result. Feel free to use the slider and adjust your result. As I mentioned before, so this is the non-dimensioning topology optimization that I just ran. So we get a rod-shaped result, which is very discrete. All right, and the mesh doesn't look super nice, so I will just quickly smooth it to get a better looking mesh. Enter smoothing strength, and now we have something that looks a bit nicer. All right, I'm happy with that result. And this is our output. We reached the end of this workflow. Maybe we can just check out what the other stream looks like. Have a check. So this was the dimensioning topo, which is more of a volume body, and maybe the ISO value can be a bit higher in this case. In this session, you got an insight into what steps are needed to set up a topology optimization workflow in our software. You are now able to transfer this knowledge to your own product development processes.